Welcome, everyone. Let's go ahead and get started. I expect many more to join us, but in the interest of giving full time to the seminar, let's go ahead and get started. For our distinguished lecture today, we're absolutely delighted to have Samuel Graham. He is the Eugene Gwaltney Junior Chair and Professor of Mechanical Engineering at the Woodruff School in Georgia Tech. Samuel is also a fellow of ASME, a member of Engineering Sciences Research Foundation Advisory Board for Sandia, and a member of the Emerging Technologies Advisory Committee at the U.S. Department of Commerce. Samuel, we're truly happy to have you here today, and I turn the floor over to you.
Thank you, Tony. It's my honor to be here today and to be here with friends and colleagues and have the opportunity to give my lecture. I'm going to go ahead and share my screen. Let's see if I can get this. Hopefully you can see this okay. What I'm going to talk today about is some of the work that we're doing to help advance the future of wide bandgap electronic devices. And I'm going to talk about it from the perspective of the development of materials, manufacturing, and the metrology, everything that has to come together in order to help us push this technology forward. If I really go into this talk, you see my name here on the title slide. I have to give credit to a lot of people that I've been working with over the years, especially my students and former students in Georgia Tech. Zixing is currently a postdoc in David Cahill's group there at UIUC, and so you'll see some of his work today that we've been doing together. Jingjing Shi, Luke Gates, George Pavlidis, Chao Yuan, Robert Montgomery, and then also Professor Alan Doolittle at Georgia Tech. And you'll see a host of others that we've had the opportunity to work with, from growers, device fabricators, material scientists, and others. And so it provides for a rich body of work in order to tackle such a difficult problem. So when we look at sort of the drive for wide bandgap electronics, one of the major drivers is in the area of power electronics. And so we start looking at the electrification of engineering systems. We understand the development of electric vehicles, charging. There's a push now to look at electrification of aircraft for transportation technologies. There's also a push all the way down to looking at efficient power control at the circuit breaker level. So you would actually have, instead of mechanical circuit breakers, you would actually have solid state. And there are many other applications that you can look at in terms of the efficient power control for the grid, mobile, transportation, spacecraft, things like that. And so there's this need to have electronic devices that can actually do the power switching, can do the power control very efficiently, small, compact form factors. And there's a lot of work that's also going on at UIUC, I understand, through the POETS, ERC. And so there's not a lot that needs to be said in terms of some of the motivations here. We also understand that wide bandgap is also being used for RF communications. So you're seeing a lot of that in areas like 5G, radar systems, satellite communication links. There's also optoelectronics in terms of laser diodes, and of course, white light, solid state lighting. And so I won't talk a lot about the solid state lighting portion of this today. I will cover sort of some of the developments that are going into pushing the technology for RF as well as power. So if I use this slide just as a way of sort of motivating, well, where are we trying to go with our power devices, and why do we need wide bandgap materials? If you look at a power switch, basically when a power switch is in the off state, you want it to be able to withstand the voltage that's being applied without breaking down. And so it needs to have sort of this infinite resistance, if you would say, in an ideal state. But when you turn the device on, you need it to switch from that high resistance state to something that ideally would be very low or zero resistance, so that you don't dissipate power while the device is on. Obviously, this doesn't happen. So during that switching state, you have power that's being dissipated during the switching state. While the device is on, you have an on-state resistance that dissipates power, electrical power. And then in the switching off state, you again have this spike of energy that's being dissipated. And so there's a lot that goes into designing circuitry, but then also looking at materials that can minimize some of these losses. And so this state right here, when the device is on, is called the specific on-state resistance. And so if you were to look at this graph right here, it gives you a number of materials, starting out with silicon, which is the most widely used power electronic device or material. And you start moving in terms of band gap to these other materials like silicon carbide, gallium nitride, beta gallium oxide, all the way to diamond. So if you're to look at this, this graph, you can see that for a given breakdown voltage, let's say if I'm here with silicon, if I move to a wider bandgap material, then my theoretical specific on-state resistance would be much lower. And then if I move again in terms of moving up in bandgap, again, it drops. And so this, this breakdown voltage versus specific on-state resistance allows you to design devices, shown here, that if I go to a device made out of silicon and I go up in the critical field and breakdown voltage, I can make a device out of gallium nitride, theoretically, that would be 9% of the thickness of silicon. And if I go to gallium oxide, now it's only 4%. Of course, these are the marks, these are the figures of merit that are being based on unipolar devices, and that's sort of where we're pushing. And so if you were to look at other figures of merit, this is the Valiga figure of merit, which minimizes resistive losses, which is basically this graph. You also have high frequency for basically RF devices. Again, you could see this Valiga figure of merit for high frequency minimizes switching losses. And then there's switching delays. And so if you look at this graph right here, we normalize everything to silicon. Silicon's 1. You can see as we go to silicon carbide, GaN, to beta gallium oxide, you could see how the Valiga figure of merit increases. And you could also see how the Johnson figure of merit increases, as well as the high frequency Valiga figure of merit. So all of these factors point towards the fact, all of these, let's say, figures of merit point towards the fact that going to higher bandgap materials or wider bandgap materials should give you some advantages. However, when we start looking at where we are today, going from silicon to silicon carbide to gallium nitride to beta gallium oxide to aluminum gallium nitride, what we're seeing is that there's a lack of large area native substrates to grow on. So that's going to give us some issues in terms of how do we grow once we move past silicon carbide. And then also as we start getting into ternaries like algan and we start getting into beta gallium oxide, the thermal conductivity starts to drop, and it drops very, very far. And so now we're going to have issues in terms of thermal. So even though we have these nice figures of merit, we're going to have some issues that we have to deal with in terms of the engineering and in terms of device integration into packages. So if I start out just with a gallium nitride high electron mobility transistor, these are used for both RF as well as for lateral devices. You can use these for power. What's interesting here is that there's no doping that's needed for gallium nitride devices that are in the form of a HEMT, because I have piezoelectric polarization from this algan layer. And what that does is it draws electrons very close to this interface between the algan and the GaN. So I get what's called a two-dimensional electron gas. And so I don't have to dope this. I just based upon the structure, I can basically create a nice sheet charge of carriers that I can then manipulate and basically form my device. So we get very fast switching speeds, high power handling capabilities. And so this is really nice for these types of devices. But as I said before, due to the lack of large numbers of native substrates, you typically have to grow this material on top of another substrate. And so that's going to introduce some challenges when we start looking at power dissipation. And so where does the power come from? And so when we're flowing basically current through this two-dimensional electron gas, I could basically pinch off this gate, which depletes my channel, so I don't have carriers in the channel. And as I manipulate the negative voltage here on this gate, I can begin drawing electrons or carriers into the channel that causes the current to flow. And so what happens here is that right here at the drain side edge of the gate, because of this large field right here, I get heating, joule heating that occurs right here at the drain side edge of the gate. We know this. So this is where the heat generation is all occurring. I can spread this out. So depending on the voltages I'm putting on this device, I can manipulate the shape and the size of that heat generation zone. But nonetheless, it's typically most intense right there at that drain side edge of the gate. And that's what we need to dissipate. So again, here's my image of my hotspot that occurs right here at the drain side edge of the gate. As I said before, I may have to grow this on a non-native substrate, something like silicon carbide. People have chosen this because of the high thermal conductivity of silicon carbide, being on the order of about 400 watts per meter K versus about 180 for GaN. And so we're going to look at heat dissipation that moves from this region down through the substrate. But again, there's a lot that has to be done right here at this interface in order to make this work. What we do know is that if you don't manage this properly, you get degradation in the current, say the drain current versus voltage. This is a fresh device versus a degraded device. We've also seen instances of cracking that occurs at this gate edge and pitting that can occur at this gate edge. So there's a lot of things that will happen in the vicinity of these high fields that occur in these devices. And so that's why we want to make sure we dissipate heat. And we also want to control the electric fields in these devices because of the piezoelectric nature of the material. So here's sort of getting back towards the, say, more of the mechanical engineering part of it. What we're looking at now is really an issue of thermal resistances. And so I have a device, it may sit on top of a power substrate. The substrate may have a heat spreader on the bottom, and then I go to a heat sink cold plate. This is typical device thermal management engineering that you'll see. What I'm going to deal with today is primarily starting here at the device level. I won't present any of the work that we're doing on this packaging portion and show you where the development of materials and the development of this device architecture really plays into the type of heating that you'll see, such as this hot spot right here at the drain side edge of the gate. This is a simulation. You can have multiple gate fingers, but all of these things come together that we have to really understand at the material level. The interfaces, the thermal conductivity of the various layers, and the device architecture is going to play a big role in terms of the overall device heating, as well as stresses in these devices. So when I look at these structures, the types of structures we'll have are what we call hetero epitaxy. So this is where I have to grow a material on a non-native substrate. And the magic that is done here in terms of the device growers, because of the lattice mismatch between a material like gallium nitride and silicon carbide, you basically put another layer in between, in this case, aluminum nitride. And this is it's been done for a while. Hiroshi Amano at Nagoya University in Japan. This is what he actually did in his PhD thesis in order to grow electronic grade gallium nitride. And this is part of the work that led to the Nobel Prize of winning the blue, for the blue LED, which led to white light LEDs. So this layer right here is very important that's being put in into practice when they grow GaN on top of silicon carbide or other materials. There's also hetero integration. So now I can place a material such as GaN on top of silicon carbide or a diamond without growth. And this is done using things like plasma activated bonding. And so this gives me a different way in terms of manufacturing, in terms of how can I put these two materials together. I can separate the optimal growth of the two materials and then place them together through a bonding method. And it doesn't necessarily require the same control that you have in terms of placing these inner layers. And then I have monolithic devices, which are basically now made from bulk crystals. I may have some epitaxial layers that I grow on top with dopants, but typically these are all made out of the same material. And so I make vertical devices out of these structures. And so I'm going to focus a little bit more on these two, hetero epitaxy and hetero integration today, as opposed to the bulk monolithic. So let's start into the materials and manufacturing challenges at the die level. And so one of the ones that we saw early on in some of our work, this is one of my former students, Luke Yates, who's currently at Sandia National Labs. In looking at RF devices made out of gallium nitride, again, silicon carbide substrates are quite expensive. So there's a push to look at, can we place these on top of silicon, which has a much lower cost? What we do know is that we're going to give up quite a bit in terms of thermal conductivity, so that heat dissipation that you would want to see from silicon carbide. So we're going for cost and giving up that thermal conductivity. And then we also know that there's a CTE mismatch between gallium nitride and silicon that leads to very large residual tensile stresses. And so it's not so simple to just take gallium nitride and grow it directly onto silicon, because it's not the same crystal structure, the CTE mismatch, other things that come into play. So what's typically done in the industry in order to control this, or in order to grow this, you basically take 111 silicon, you have to put this inner layer here again, just like I showed you before, between GaN and silicon carbide. So this is aluminum nitride that can be grown here, and then you can grow electronic grade gallium nitride on top. What we have seen in some of our measurements is that the thermal resistance of these inner layers here, when you have this structure, is on the order of 20 meters square K per gigawatt or less. So it's actually pretty good. but the issue is that the large tensile stresses can lead to crack formation. So it limits the amount of GaN that you can grow on top. If you grow it too thick, you'll actually get crack formation. So what others have tried in order to actually grow very nice gallium nitride layers on top, they use a superlattice structure made from gallium nitride, aluminum nitride, and some other layers here. And so what this allows you to do is control the stresses. You can grow thicker GaN, but now you're trading off with a much larger thermal resistance of this entire stack. So I can grow thick GaN with poor thermal resistance, or I can grow thin GaN with, high thermal resistance with the thick GaN, or I can grow thin gallium nitride with very, very low thermal resistance, and I have to trade off the stresses. So what we've been able to do is working with some commercial companies, looking at what happens as you grow gallium nitride on top of these superlattice structures, and as well as on top of the aluminum nitride. So this is just showing you with the gallium nitride going from 0.3 microns out to 1.27 microns, you can actually see the stresses in the GaN increase. You can see the bow of the gallium nitride, of the wafer also here increase. And so what I'm doing here is I'm using Raman spectroscopy as well as photoluminescence. Why do we use those two measurements? Raman spectroscopy gives you the average through the thickness of the GaN. The photoluminescence gives you the stresses right at the surface. And so I can begin to look at gradients and the stress gradients in the material. But nonetheless, what you see here is that you start having these very, very large stresses. When I use the superlattice structure, what's interesting is that it goes compressive, but right here at the surface, it's close to zero. So there's a lot of things that you can do to manipulate the stresses in the gallium nitride to make this work in the trade-off for increased thermal resistance. The other thing that we do worry about is that the AlGaN layer, which is about 20 nanometers right on top, it undergoes what's called pseudomorphic growth, which just means the lattice of the AlGaN takes on the lattice of the gallium nitride. It's stretched. That's all we need to know, is that it's going to be under a tensile stress. And so we're basically now just sort of calculating what the stresses are in the AlGaN layer and how it drops when you get to this pseudomorphic growth on top of this superlattice structure. And so these are things that are very, very interesting for us to go through to improve the overall reliability of the devices from a mechanical point of view. So now what we want to do is take a look at, well, what happens from a thermal point of view when we do this? And so here, what we've done is you're using a two-finger device. So basically, this is my source, gate, and drain. So I have a dual structure here. So I have two channels, and I can go through and do some measurements. And so we'll have these sitting on top of superlattice structures in order to see what happens. We're going to use Raman spectroscopy. Here's a nice technique that you can use to measure temperature. And so how does this actually work? When I use Raman spectroscopy, I have a laser that can actually go through the material because it's transparent to my laser wavelength. I still get scattering where I get a peak that is for silicon. I can also say peaks that are for gallium nitride. I see two peaks here. And then also I can put nanoparticles on top, which are TiO2, which don't impact the electrical performance. So what this does is it allows me to measure the temperature right at the top of the device, lets me measure the temperature all the way down here at the silicon, and this allows me to measure the temperature inside of the GaN. So now I get this vertical measurement of temperature through the device. So here's what's quite interesting. So now I have a 5 micron thick superlattice structure here, about a 2 micron thick GaN layer, and I'm powering this and increasing the power here. And so when I use Raman spectroscopy, I can see the temperature rise in the silicon. When I use the same technique, matching the fingerprint to the GaN, you actually see a much larger temperature rise in the GaN. This is quite interesting. And so when I look at the top temperature of the TiO2, this is what you see. So you see, again, the temperature at the very top is slightly larger than the average temperature. So that's what we expect to see. But there's this huge drop between the gallium nitride and silicon. And we believe that's coming from this superlattice structure. So going through and doing modeling and some measurements. And so in this case, we measure the thermal conductivity of the superlattice structure. You can see that it has a very low thermal conductivity on the order of 7 watts per meter K. We measure the thermal conductivity of this thin gallium nitride layer. It's on the order of 104 watts per meter K. And you put that into a model, and basically what you see is that you do get a reduction in temperature between the two. So I have a superlattice structure, it's going to be hotter than if I don't. But what you also, again, you see this confinement of the heat really close to the channel region, whereas this is spreading out. So this is giving us an idea that we need to build in some heat spreading into the device structure in order to counteract the need for this superlattice structure, which is basically helping us to control stress. And so now moving on to thermal reflectance, what we've been able to do here is use transient thermal reflectance. We're actually watching this 2-finger HIMP, the gate structure, heat up. And so you can see this is 100 nanosecond time steps. And so you can see we do very, very high speed imaging of the heating of the device. And we could also see qualitatively the heating that occurs in the channel. And so we're going to use this technique to sort of image thermally what happens to the temperature on the gate when I have superlattice structures and when I don't have these superlattice structures. So here's the first one. So I have a thick superlattice structure. I thin this by about a factor of 2, not quite. You can see that just basically qualitatively, the temperature is going down. And now I have this algan structure, again, this highly tensile version, and you can see the temperature is the lowest. So this is exactly what we'd expect, the thick superlattice structure versus thin superlattice structure versus no superlattice structure. The temperature is dropping. So this still doesn't help me in terms of fielding these devices with the superlattice structure while cooling them. So the technique here is in order to introduce some heat spreading, what we're looking at here is, can we take the fact that the stresses are controlled by having the superlattice structure, grow a much thicker layer of GaN, which I can't do in the other device, to actually enact heat spreading. And so here are the results. And so when I have this particular structure with a superlattice structure here, I'm fixing, say, this gallium nitride layer. You can see the temperature rise here is on the order of about 70 degrees C temperature rise. If I increase that GaN layer thickness by a factor of 3, you can see it drop. And so this is one of the signs that shows you that, yes, you can build in this heat spreading. You can do this co-design of based on thermal resistance, stresses, and heat spreading inside of the device architecture. Plus, this also helps you if you want to move more into power devices and not just RF with these particular structures. So here's just sort of a summary. This is it was sort of an interesting mix of various parameters. I have a very thick superlattice structure. I have gallium nitride on top of this structure. You can see that this structure actually has the lowest temperature. Then if I were to actually take this gallium nitride, thin it down, as well as thin down the superlattice structure, I actually get a higher temperature. And so again, this just shows you that there's interesting co-design aspects that have to come into play when you start looking at how these structures will behave. Okay, so now I want to move on to something that's a little bit more high power, also challenging. So we're going to move to gallium nitride on silicon carbide, gallium nitride on diamond. And so again, what we talked about earlier was the need for this inner layer right here to help with the growth of high quality gallium nitride for electronic grade structures. And then if I were to move to GaN on diamond, again, we do this because I can go from a material that has a thermal conductivity of 400 watts per meter K to something here that's 2000 or higher. And so to help me dissipate the heat. But again, this lattice mismatch says that I have to put something here in order to be able to grow these, in order to do some sort of growth, to have these come together, because I can't grow the gallium nitride directly on diamond and get electronic grade material. So these interfaces are going to play an important role. So one of the things that we looked at in our research is, first of all, we know that we can make high quality gallium nitride on other substrates. Can I remove that and actually bond it directly to silicon carbide without this inner layer? And so this is done through what's called plasma activated bonding. We're interested in this technology because it's shown over here on the right. You can see we can do this at wafer scale. So this is actually what's done to some degree in SOI wafer production. So can you adopt this for heterogeneous integration of two electronic materials that you typically don't grow together, or you can't grow together in the fashion that you're trying to bond them? And so here we have gallium nitride grown on sapphire. You can actually take this, use an argon ion beam, you can activate the surfaces, place them together under pressure, and then do a laser liftoff of the sapphire. And now you're left with this gallium nitride on this substrate. You can then do a smart cut to remove some of the gallium nitride to make it thin. And so we did this portion to make it thin in order to do thermal measurements of the thermal boundary resistance between the GaN and the underlying silicon carbide. So the interesting thing here is that we're trying to get rid of the interface of the aluminum nitride, but going into doing this plasma activated bonding, what you end up doing is you damage this interface and you end up getting an amorphous region of silicon carbide. So we still don't get away from having this interfacial region between the two materials. What you are able to do is anneal this at about 1000 degrees C, and you start to get recrystallization of this interface. And so it's still not perfect, but this is something that can be worked on in terms of the manufacturing processes in order to improve that overall interface in terms of the crystallinity. The other aspect is that if you go and do TEM imaging plus chemical mapping, you can also see what we found is that you end up getting argon atoms that are actually trapped at this interface. And so this is sort of discontinuous after the annealing. If you don't do the anneal, it's actually sort of a continuous layer of argon that's actually trapped here at the interface. And so there's still some room to understand what this might be doing and how that might play a role in the recrystallization as well as the thermal aspects of these interfaces. But again, this is looking at the limitations you have in terms of a wafer scale process in terms of bringing these together. Now here's the nice information that we're able to find out. So when I grow this material on sapphire, I can actually grow high quality gallium nitride that I can then bond directly to this silicon carbide layer. If you do MBE growth directly on silicon carbide, what you see is that you actually get a lower thermal conductivity because it's not the electronic grade version. So we're able to get fairly high or fairly good thermal conductivity of this particular layer. But what you also see is this comparison at the as bonded. If I look at the thermal resistance or the thermal boundary conductance between the GaN and the silicon carbide, it's lower than if I grew it with MBE on the aluminum nitride on top of silicon carbide. So I'm not doing any better here. But after I do the annealing, what you see is that we end up getting values that are very high, which are on the order of what you would see with MBE growth directly on silicon carbide in terms of that thermal boundary resistance. So this work, again, this was from Z, who's currently a postdoc there in the Cahill group. And so you can see that this is one of the highest values that we've seen for thermal boundary conductance from gallium nitride to silicon carbide. But yet in this particular case, we do have the electronic grade material that could be used to make devices. What this also points to is that this plasma activated bonding, which we've actually tried with other materials, which I won't have a lot of time to go into, can be used to integrate, mix and match other semiconductors with high thermal conductivity substrates. So it's opening up this toolbox to begin using manufacturing techniques to begin integrating thermally dissipating substrates or heat spreading substrates with these materials that are actually producing a lot of heat from joule heating when the devices are operating. One of the things I will have to admit though is that what we have shown you here is GaN bonded to silicon carbide. Typically, if you're going to go and produce this, because of the polar nature of GaN, you want to have, when it's grown on sapphire, you want to have this surface up. So typically what you'd have to do is go back, bond this to a handle wafer, and then take this and bond it to the silicon carbide and take the handle wafer off. We did not do that in our research experiments, but this is something that can be, it's an extra step that can be done in industry. It's currently being done with GaN on diamond, and I'll show you some of that in the next set of slides. So why move to GaN on diamond? As I mentioned before, this is GaN on diamond gives you this high thermal conductivity material that should be great for dissipating heat. Here's a device that we modeled. This is GaN on silicon carbide. You can see each one of these channels that are spaced apart by 50 microns. I can actually place this on top of diamond according to my modeling and place these now only 10 microns apart. And what you end up getting is basically this device, the channels are no hotter than this one over here because of the diamond helps with heat dissipation. We were able, working with Raytheon and others on our DARPA NJTT program, we're able to demonstrate that you could take this GaN on silicon carbide device, shrink it down by a factor of 3, and this device is not hotter than this one. And so there's a very interesting effect of going to diamond in order to help dissipate this thermal energy. So how is this done? Again, let's go back to our carrier wafer that I mentioned before. I have my GaN that's grown on silicon carbide or aluminum oxide. I'm going to bond it to this carrier wafer. And then what I'm going to do is remove it. So there's various techniques to remove the gallium nitride. And then in one case, I'm going to place diamond seeds on the back, and I'm going to grow diamond on the back of the gallium nitride. This is probably the more common technique that you see with people that are producing GaN on diamond. And then you remove that carrier wafer. In the other case, I would have this on the carrier wafer, and now I'm going to do bonding. So as I showed you before, plasma activated bonding, trying to get rid of these interfaces. And now I have a transfer bonded GaN on top of diamond. What we do see, again, these inner layers, this is what is causing a lot of the issues or the limitations in terms of moving heat from the GaN into the diamond. Even though this is a very, very high thermal conductivity material, this is what you have to worry about. So what we've done here is looked at the impact of some of these interfaces on the thermal transport behavior. And so I have GaN, I have diamond, I have the silicon nitride, which is commonly used. So we said, what if we take the silicon nitride and just thin it down to 5 nanometers? What if we replace the silicon nitride with aluminum nitride, 5 nanometers? And then what if we take this sample and we don't have an interlayer material and we grow the diamond directly on the gallium nitride? What happens? So this is a graph that shows you basically, here's the thermal conductivity or the thermal resistance, thermal conductivity of the diamond layers, the thermal resistance. There's not a big change between the diamond grown on any one of these interfacial layers. We're measuring this using time domain thermal reflectance. The thermal resistance between the aluminum and the diamond, that's not where you see the change, but what you do see is a large change in terms of thermal boundary resistance between these. So what's happening? So if I try to get rid of that thermal interface, or you try to get rid of that interface altogether, based on just handbook calculations, you would say that the thermal resistance should go down, but it's actually going up. Well, the hydrogen that's in the plasma from the diamond growth actually begins to eat the gallium nitride, and so you introduce defects. And so this is why you have to have some sort of interfacial layer there when you're trying to grow directly. When we do aluminum nitride, we've seen some areas for this particular one that's been etched, that's been removed. And so you get some unevenness there. So we think that's where that thermal resistance is coming from. I will say the Martin Kubal's group in Bristol has worked on this a bit more, and they've been able to make this better. But this is at the time when we published this is where we were. And then you get to silicon nitride, and it has the lowest thermal resistance. So what is happening here? What we ended up seeing is that this 5 nanometer thick layer of silicon nitride actually had, you can barely see it has some etching, but it only etches down to about 3 nanometers in thickness. So you still have that silicon nitride layer that remains. It's very thin. And this leads to some of the lowest thermal boundary resistances that we've ever seen between GaN on diamond. And so thermal boundary resistances on the order of 10 to 12 meters squared K per gigawatt, or in terms of conductances between 80 to 100 megawatts per meter squared K. And so I want you to keep that in mind, this number right here between 80 to 100, as we go to, obviously, how would you bond these? That's the other step. Can we do it the other way? And so here's an aspect of taking gallium nitride. We want to remove the silicon nitride, and we want to bond directly to diamond. Well, that's actually not so simple. So what we try to do in working with our collaborators is place a layer of silicon on top of the GaN, a layer of silicon on top of the diamond, plasma activate that and bond it, or you mix a silicon containing precursor in the plasma, so you sort of co-deposit the silicon while you're activating the surfaces and bond. And so again, this is work that was just published last year. And so we're able to successfully bond the materials together that way. And so this is what you see. If I deposit the silicon layers here, you basically get some amorphous layers that are actually occurring. You typically see this amorphous carbon here. You get some more amorphous areas, and you get the silicon layers. If I do the in situ, you will also see, I don't have the TM showing you, there's still some amorphous layer here. You get a very thin layer of a silicon containing material. But what you do see is that for this sample here with the thick inner layer, you're down here around 60 megawatts per meter squared K. Remember before I said some of the best was between 80 to 100. And so now when I do this thermally activated bond, this plasma activated bonding, I'm sitting here around 90. So I'm right in that sweet spot of having some of the best thermal interfaces that's been reported. And there's still a lot of room to grow in terms of dialing in these process parameters to control the amorphous layers. In this case, we're not annealing it in order to get rid of this amorphous layer. So there's quite a bit that we can still try to do in order to use plasma activated bonding in order to produce extremely low thermal interface resistance combinations of heterogeneous materials. So another thing that comes up, if you go back to what I said about the GaN on silicon, we were worried about stresses. So here, we're also going to worry about stresses with the diamond. So we're going to use a couple techniques. We're going to use, number one, we're going to use Raman Spectroscopy. And I showed you before, I can get these two gallium nitride peaks. And these peaks will move with both temperature and stress. So when I do this measurement with Raman spectroscopy on these materials, I'm going to do this at room temperature. So any shift in the peak has to come from the stress component as well. So we'll see a shift in the frequency of the phonon peak that is linearly related to the stress in the film. And so we've gone through and we figured out these correlation factors, the K here. The other one that I'm going to show you is photoluminescence. Again, the band gap of the material will also shift with strain or with stress. And so I can also use photoluminescence to measure right at the top in order to get a stress measurement at the top of the device. So here I have my gallium nitride on diamond. What's nice is that the diamond is transparent to my UV laser. So I can measure the surface stress right here at the back side with PL. I can measure the surface stress right at the top side using PL. I can measure the average stress through the thickness. So what we know, and again, using this technique, we know that if I have a film where my epitaxial layer has a CTE higher than the coefficient of thermal expansion of the substrate, my film is going to be in tension. And so if I grow GaN on, so if CT of the epi layer higher than the substrate, if I grow GaN on a material like silicon here, I know I'm going to start out with a tensile material. If I grow GaN on sapphire and I try to transfer it and bond it, I'm going to start out with a compressive material. And so that's what you see here. So when we start out, we have GaN on silicon epitaxy. I do the transfer bond, even though I'm doing the transfer bonding at low temperatures. What we see are these very large stresses that can exist in the gallium nitride. Or excuse me, I'm sorry, this is the growth. I'm sorry, I'm going to get to the transfer bonding next. So this is the growth. And so I get very, very high tensile stresses near the top surface. It can go compressive. There's a lot of work on, again, dialing this in to reduce these stress gradients. As I grow GaN on top of silicon epitaxy, I use that to then grow the diamond on the backside. So that was that carrier wafer, removing it from silicon, growing the diamond on the backside. This is what you're seeing, these large stresses here in these devices. If I grow GaN on silicon carbide, and now I do a low temperature bond, you see the stress gradients are much smaller. Now, if I do the plasma activated bonding that I showed you earlier with that silicon interlayer, what you see is that the stress gradients are really small, but now I flipped it to being compressive. And so I would say that these are fairly early results. We have not, we're actually in the process of putting these out. So we haven't quite published all of these yet, but we're in the process of trying to figure out, again, from a manufacturing point of view, we know that we can combine with diamond. We know that that gives us very good thermal performance. But now, how do we go through our manufacturing techniques to begin dialing down those stresses while still keeping a very good thermal interface? And so these methods of using photoluminescence and Raman spectroscopy come into play a very important role for the stresses, as well as the TDTR and the transient thermal reflectance for understanding the thermal response, as well as the thermal properties as we do this heterogeneous integration. So now I want to move into the very last portion of the talk, just to sort of give you some future stuff. And so when we move from GaN, I've talked mostly about GaN this entire talk. We want to start looking at, well, what about beta gallium oxide, which a lot of people are jumping into, and aluminum gallium nitride, which there's even a call out now from the Army Research Office on this material. And so the interesting thing, as I said before, is that we look at the specific on-state resistance for power. As you start moving up your band gap, we saw that there's this benefit. So I won't go over this again because we already talked about it. But the beta gallium oxide, what's nice is that it's grown from the melt, so you can get fairly good large area substrates for beta gallium oxide. Not necessarily cheap yet, but it's readily available. You can buy these commercially, doped with various dopants, even semi-insulating. And so there's this nice push in terms of the thought that the price is going to come down, but there's still a lot of work to be done here. I'll show you the challenges next. And then algan. So you can grow these on aluminum nitride and sapphire, which are, again, readily available. And again, you look at current densities. The current densities of algan transistors actually can be higher than that of gallium nitride even at today. And so these are very interesting things, but when you start looking at where do we start running into problems, the thermal conductivity of beta gallium oxide, now we're talking about it being highly anisotropic. The highest thermal conductivities in the O&O direction is on the order of about 26 to 27 watts per meter K. This is 10 to 100 times smaller than other wide bandgap materials. When we move to ternaries like aluminum gallium nitride or aluminum gallium oxide, we're only finding a very few reports in the literature that even talk about the thermal conductivity of these materials. So algan materials, the thermal conductivity is closer down here to about 10 watts per meter K, 10 to 15. What we have seen with algo is that the few reports that we have seen, the few numbers, they can be as small as 3 to 5 watts per meter K. This is a measurement that was again done by Z, where this is superlattice structure with just a 10% algo composition. And this material, this superlattice stack right here was about 4.7 watts per meter K. So there's still a lot of unknowns in terms of what the thermal properties are, the temperature dependence, the thickness dependence, all of these things, and the compositional dependence of these materials. And what you're seeing are a number of device structures that are going to be dependent upon having these ternary oxides or these ternary nitrides as they begin to push towards high RF or high power device level operation. And so there's still an open area of research that needs to be done here in this structure for these structures. We have looked at, well, if you can't really manipulate and increase the thermal conductivity of these materials, which we're not going to do, what you have to look at is the overall packaging structure, the packaging architecture. And this gets into, all right, can you just simply take gallium oxide and put it on top of diamond and cool it like we're doing with gallium nitride? Well, the answer is yes and no. So if I have a very thick layer of gallium oxide, the majority of my thermal resistance comes from the gallium oxide, and it really doesn't matter what I put down here because this is going to cause my the thermal resistance, which is going to raise my temperature. But if I make it really thin, you can see that as I make it thinner, then the substrate thermal conductivity comes into play. So that's the structure that we saw mostly with gallium nitride. But the other way to do it is to basically package it where you have a thermally dissipating substrate very close to the top side of the device. You're looking at underfill materials, other things like this, so that way you can dissipate the heat out through this structure. And that's where sort of the current areas of research are in terms of developing new materials to enable these kinds of architectures. The other one is to, instead of using sort of these lateral devices, to go to fins, so FinFET structures. We've seen this in silicon. And again, these die-attached materials that are here, again, for pulling this heat out of the structure. The thermal conductivity does play a role at higher powers of these die-attached materials. But again, this dielectric material that you put inside of here, this is where you're going to see the biggest benefit. So you see most of our dielectric materials are down around 1 to 2 watts per meter K. If I can create dielectric materials that even have a slight increase in thermal conductivity, you're going to see this temperature begin to drop quite a bit. And so again, for these trench MOSFETs or these FinFET structures, this is where a lot of the action is in terms of where do we go. And then again, you start looking at contacts. So these metal contacts here, you could also, metal contacts. So here we've actually been able to do the same plasma activated bonding, taking gallium nitride thin layers, transfer bonding it over onto silicon carbide. And we've also been able to do this with diamond. And then you could also look at direct MBE growth on silicon carbide. And this actually gives you a slightly better interfacial thermal resistance of gallium oxide growing directly on silicon carbide than even the bonding because of these interfacial materials. Again, this is some work where we placed this on diamond. This is some work that we did with the Naval Research Laboratory. They were able to achieve power densities of 60 watts per millimeter with these transferred over to diamond. However, the thermal boundary conductance here is only 17 megawatts per meter square K. We believe that you can dramatically increase this in order to improve the overall heat dissipation from these structures. And so I want to go ahead and start wrapping up. The last one that I'm going to mention here is as we begin putting metals down, again, we can deposit metals by things like E-beam evaporation. We could also deposit metals by MBE. The interesting thing that we've been finding in our work is that when you deposit metals by MBE, you actually get this dramatic increase in the thermal boundary conductance. And part of this, we're looking at the chemistry at the interface of how the metal's interacting. with materials like beta gallium oxide. It's not just beta gallium oxide. We've seen this with other materials as well, depending on how we're depositing it and increasing the thermal boundary conductance. But here with beta gallium oxide, you start getting these interfacial reactions. And so again, as you try to do this, how do you control these reactions in order to maximize the thermal boundary conductance on these particular structures? So I'd like to go ahead and conclude now and have the chance for any questions, but hopefully what I've shown you here is that wide bandgap semiconductors are being pursued because of the promising figures of merit, also the growth in the availability of some of these substrates like beta gallium oxide. And there's a lot that's being done in order to try to push these technologies for the future of RF power, as well as optoelectronic devices. I didn't talk about solar blind optoelectronics that can be done with beta gallium oxide. However, as you can see, there are some challenges. So knowledge of material and structure property relationships, mainly the thermal conductivity and thermal boundary conductance, along with co-design methods where we consider the electrical performance, the mechanical behavior, as well as thermal. This is going to be key to pushing the technology forward. We can't just design a thermal solution and hope the other two will work out. Manufacturing for heterogeneous integration will be an enabler for the future technologies. We're looking at plasma activated bonding. We're looking at other growth techniques for how we will actually put these various materials together and understand how they will behave inside of the device. And these are things that require a lot of material science modeling, as well as the kinds of measurements that we've been doing. And then finally, in order to make beta gallium oxide and AlGaN technologies work, it's going to require aggressive cooling technologies that are integrated at the chip level. And this is a wide open area. It will require a true multidisciplinary effort between teams of scientists and engineers. And this is where we're trying to have a lot of fun today. So with that, I'd like to thank you for your attention and answer any questions you may have. And again, I really appreciate the opportunity to come here to speak today. Thank you.